Take it away.
Good morning, everybody. My name's Gus, and I'm the theory expert, I suppose, expert in Dr. Mellon's modern physics class. So, the minimally supersymmetric standard model.
You might not want to stand directly in front of this.
Sorry.
Oh yeah.
The minimally supersymmetric standard model predicts 5 Higgs bosons that account for the electroweak symmetry, providing the distinct, massive electromagnetic and weak forces we observe. Recent research suggests that the 125 GeV Higgs discovered in 2012 may in fact have a lighter sibling at approximately 98 GeV. Our experiment this semester has been given simulated data to determine whether or not this little Higgs exists and its broader implications in supersymmetric theory. So, to make our little Higgs, we determined the Higgs-Stirling production mechanism is the most accurate and viable method of production. As seen in the Feynman diagram to the right, the collision of Higgs-Stirling production via the collision of 2 protons results in a W boson in our little Higgs. And as opposed to vector boson fusion, gluon fusion, and associated production, this mechanism is ideal because it produces a relatively low background noise while producing a clear signature. So, our little Higgs will decay into a bottom quark, anti-bottom quark pair, which result in jets, and our W boson in our ideal signature decays into a lepton and neutrino. Our ideal signature, therefore, is 2 jets, a lepton and the missing transverse energy corresponding to the produced neutrino. Thank you. Nick.
Hello, I am Nicholas Inocencio, and I am the expert on track identification. And so after I got the coordinates for hits recorded in the silicon tractor detector, I put them into Excel and made some 3-dimensional and 2-dimensional scatter plots. I used the 3-dimensional scatter plots to identify distinct jets and tracks. Right there, 2 jets, 1 track. And so using that information, I could compare that with my 2-dimensional scatter plots and see which one distinctly showed 2 jets and 1 track. And so then I used those 2-dimensional scatter plots to determine, and then I translated all the points so that the interaction point occurred at the origin of the graph. That way, I can use the arctan function of Excel to sort the points based on the angle that they made with the horizontal axis. And that's a very good way to distinguish which points are part of specific jets and tracks. And a couple samples. Here I've got 1 sample. Here I've got a jet and a track, and that's the example from the first slide. And then here I've got 4 jets. Moving that way to that way and down. Thank you.
Hi, I'm Abby Paul, and I use the CMS electromagnetic calorimeter to find the energies of electrons and photons present in the 10 events. When I received the data, I first set an energy threshold of 6.24 times 10 to the negative 8 GeV. This eliminated a lot of the background energies while still allowing me to see muons, which gave me a better idea of what was going on in the events. So first I divided the data by their z values so that I could find the negative end caps and the points in the central area. I then converted the points in the central area to spherical coordinates and graphed the end caps on x and y graphs and the central points on phi and eta graphs. My results were that there was 1 electron in event 0, 2 photons in event 4, 2 electrons in event 5, and 1 electron in event 7. Electrons that were shot down the beam pipe couldn't be measured.
Hello, my name name is Kikadama, and I analyze hadronic interactions in the hadronic calorimeter. So when looking at these interactions, I often compare the data with the z-axis versus the x-axis, because often, especially for jets, the energy clusters split themselves between different areas on the z-axis. For example, on this graph, there was one jet that had most of its energy clusters on the graph at negative 3.88 meters on the z-axis. Another one, which is like at the front plug calorimeter. Another one had all its data points at the end plug calorimeter, and then the third one had all its energy clusters in the center in the central calorimeter. The way I organize it, the energy clusters by which particle they correspond to, was by finding the highest energy clusters, and then figuring out based on the graph of z-axis versus x-axis which energy clusters correspond with those high energy clusters, and then I organized it by the region. Like this is a sample of it. So I had organized it by the highest energy events in those different regions, and the lower energy readings could often be ignored because since they were such small energies that it wouldn't affect the final measured energy in the end. And for events that had muons, they were often more difficult to determine where which energy clusters correspond with which particles, because they were often at lower energy, so it was difficult to determine the first higher energy clusters. So on this one, I split the graph. I analyzed it versus the z-axis versus the y-axis, because there's two muons in this interaction that occurred in that interacted in the central calorimeter, and one of them had all its energy clusters where y was greater than 0, one was where y was less than 0.
Hello, I'm Julian LeBlanc, and I'm the expert in muon detection. I was given 10 different events in which there were coordinate points for the different hits in the muon chamber. I then took each of the events and graphed them in Excel, and I made 3 different graphs for each event, one with the x versus y, one with x versus z, and one with y versus z, in order to identify the muons. Because the muons are so much heavier than the other particles, they tended to follow a straighter line, as seen like here or here. Those are my results, with muon in different events ranging from 7 to 0, in which some of them had no particle hits at all. And so, like, as you can see, I had to identify them, the muons versus the jets, where muons were like the straighter lines and the jets were more spread out points of data.
Hi, I'm Ryan, and I was in charge of matching for this experiment. But first, before we could actually do the matching, we also needed to find the momentum based on the tracks that were given from the original data. And so what I would do is I would map the track that was a known lepton onto logger pro, and then take the equation of a circle, either in the positive or negative direction, and then fit that to the line, and whichever best fit, I would take that radius that was found, and then use that radius in the relativistic momentum equation, with knowing the charge of the magnets and also the intensity of magnets, so that I could get the momentums for them. And then I would also, on that same line, map some of the electronic calorimeter data in order to start matching up the tracks to the electronic calorimeter. And then I continued in Excel with the muon chambers and the hadronic calorimeters. And so tracks of varying lengths, I would be able to tell the direction in the XY direction in addition to the Z direction. And so I would map that on an XY graph, and then look at the path and see which ones were best fit based on the direction. And then also I would know that neutrinos and photons would not leave tracks, so I would not be looking for those. And then I also would fit the same muon stubs to the circles that were from the original actual tracks that we had from earlier. And so if they were a fit, then I would know that those muon stubs would match with those tracks from the original experiment.
Hi, I'm Mano Namaduri, and I'm the expert in particle identification. After tracks and clusters were isolated, the events were passed to me so that I could identify specifically the muons and electrons within the events. So to do this, I used CMS particle identification requirements, which were mainly focused on isolation of the tracks and clusters, but they also required some information about pseudo-rapidity and momentum of each particle. So using those different ranges, I was able to calculate pseudo-rapidity and use momentum values to find which particles were able to be used in the experiment.
Hello, my name is Joshua Rodriguez, and I was tasked with determining statistics and other things about jets. So for each event in our experiment, sometimes jets were detected, and my purpose was to determine the energy and locating the centroid of each jet in spherical coordinates. So in order to distinguish each particle into whatever jet it was, I needed to separate into various axes, sometimes XY, sometimes YZ, sometimes XZ. In this case, it was best to organize it in the X and Z axis. As you can see, the particles were separated equally, this being one jet, this being another jet, this being another jet, and this being another jet, because of their different Z values. And this was done for every single event that contained a jet and every single jet in those events. In terms of calculations, I need to calculate the energy of each jet, which was found by adding up all the components of the jet and converting it into GeV, because the calorimeter data was originally measured in joules. And then the second thing I needed to do was calculate the location of the centroid of the jet, which had to be done in spherical coordinates. So in terms of theta and phi, so theta was arctangent of x and y, and phi was calculated with the arc cosine of z and the z divided by the magnitude of the jet. Now the centroid of the jet was then calculated from there in Excel using this formula right here.
Hello, my name is Kyle Thomas, and for my part of the experiment, I was tasked with B-tagging the jets that we received from the different events. So the purpose of B-tagging is to find a better estimation for the energy of the bottom quark by looking at the redistribution of the relative energy difference across both the jet and the quark. And so, but first we need to know where the B jets are and how to distinguish them from light jets. And so as you can see in this plot, there is a gap near the origin. And that plot, gap relates to where the B quark decayed through the CMK matrix, and that's because that's a longer lifetime. It only goes through weak interactions. So the previous slide showed an example that I was given, and I was tasked with taking the jets that we got from the different events. And in this event 1, jet 3, there's a similar gap that shows that this must have that this jet is B tagged. And so, also, like Josh mentioned, have to look at all 3 planes of 3-dimensional space. In this case, it was XY that showed the gap. Even if one plot shows the gap, I would know that it was B-tagged. And in this example, I know it's a light jet. Even 3 jet 2, it's a light jet because the gap lengths are consistent throughout the entire plot, and this trend was consistent for the different planes.
Hi, my name is Catherine, and I worked with missing transverse energy. So taking data from the calorimeter towers, I calculated the transverse energies. And assuming that all the energies would sum to 0, we could assign the remaining, or the vector sum of the energies as the energy of the neutrinos. And this is an example. So those are 2 electrons, 2 muons, and the opposite of their sum is the missing transverse energy.
Hello, my name is William Drennan. For my part of the project, I did the level 1 trigger cuts on 1,000 events using the semi-leptonic IPT triggers for the W boson decay. 26,802 events were accepted, giving an overall trigger rate of 0.268, an overall muon trigger rate of 0.17, and an overall electron rate of 0.15. These are the 10 events from the previous talks. Given the data by the other groups, I calculated the transverse momentum of the particles inside each event, and using the level 1 triggers, events 0, 2, 5, and 7 would be accepted by the level 1 trigger. And these are graphs of the products in those events, and because the signal leptons are isolated, these events would also be accepted by the high level trigger.
My name is Vishal Patel, and I'm the expert in luminosity. I got data directly from the direct raw data, and I used these two equations both to find luminosity 2 different ways. The first way I did it was tower occupancy fraction, where basically I take the towers that are 0 and the towers that are not 0, and use the fraction that is not 0 in the equation to find it. And then the other way is transverse energy sum, where I use the energies and the x, y, z coordinates to find the angles, and then take the sum of the transverse energy and use that. So I did it both ways. I had the first way, like here. I used the numbers I had and put them into the equation, and then graphed it to see what the two unknown numbers were. And then I did a similar thing with the transverse energy, where I found it, and then I put it into the equation, and I got the numbers that I needed to calibrate it for the actual data, using the simulated data I had earlier. And then I used those numbers and add in the data that I had to find the transverse energy and tower occupancy based luminosities for each one. Then I removed the data from transverse energy, because the results I got were an order of magnitude too high to be reasonable for luminosity numbers, and kept the tower occupancy ones because they were within a reasonable range. And then I was told to find what the total integrated luminosity would be if there was a 50% duty cycle for a year on this accelerator. And so I took the equation with the numbers I had and then integrated it, and found that it would be about 69.47 1 over femtobarns.
My name is Rachel Harness, and I did the event selection. So I got a Monte Carlo simulation of the transverse mass and MET significance for known backgrounds, and then I also got the actual data. And you can see that the main difference between the two is that cluster of data at the bottom left, which is the QCD background. So to get rid of most of that while keeping as much data as possible, I cut everything below a transverse mass of 25 GeV, and everything with an MET significance between 1.8 and 2.2. And then the other cuts I made on the other data was cutting everything below 20 GeV for the lepton, everything from 20 to 35, and from 75 to 100 GeV on the leading jet, and everything below 35 GeV for the missing ET.
Hi, my name is Alan Yang, and I estimated the number of signal events we would expect to find. So the first thing I did was calculate the scale factor that relates the Monte Carlo with the actual data for the lepton transverse momentum cut. So since the data in the Monte Carlo behave very similarly, I was able to use a linear scale factor to match the two and estimate the real data from just the Monte Carlo. So to do this, I used 10,000 events of the Z boson decaying into either 2 electrons or 2 muons, because the interaction behaves very similarly to the cut, and the scale factor comes out to be about 98%. And I was able to use this number to calculate the net efficiency and then later the total signal events. So the number of events is the product of the efficiency, the luminosity, the cross-section, and the acceptance. The acceptance is about 1, so its effect is negligible. The luminosity is about 70,000 inverse picobarns. The cross-section is about 0.1 picobarns, and the efficiency was calculated to be about 12%. So to calculate the efficiency, I used 10,000 signal events and applied the different cuts to the events, and took the percentage of events remaining afterwards as the efficiency. And then the number of events estimated is about 800 or.
Alright, my name is Alonzo Marsh, and I am the expert on WJet events. Basically, what we did is we started by looking for our event signature, which was, as Gus pointed out at the beginning, 2 jets and 1 lepton. And then going based on that, I used data that I got from Rachel to do more cuts based on leading PT and up to QCD cut. And then we made sure everything was B-tag. This was used to calculate the acceptance rate. Unlike what Alan just did with the other jets, these jets, because WJet events, because we're looking for very specific ones, the acceptance rate came out to 3.4%. So then based on this, using the exact same equation Alan did with the cross-section luminosity that I got from Vishal, the acceptance rate and the efficiency that I got from Alan, I calculated 3,461 out of our 3,461 expected events. This is then scaled, and I'll talk about calculating the scale factor in a second. So because the data doesn't actually match when you look at experimental WJet events because they're calculated to leading order versus the actual data, what we do is we scale them using some data from the sideband. So here the little crosses on the map are where our data is supposed to be based on what you'd expect from Monte Carlo simulation. And then the red shows all of the other jets that aren't WJet events. And then the very dominant portion that are all green are the WJet events. And so calculating average scale factor that was designed to minimize error, I calculated a scale factor of 1.18, which, as I talked about earlier, was multiplied against 3,641 to calculate the total number of expected events. And this came out with an average error of 7.72% based on where you are on the graph.
Hello, my name is Kevin Hinchalong, and I'm the expert on the other backgrounds. So my job was to estimate the backgrounds including the W plus jets. So the main backgrounds we were concerned about were the TT bar events and QCD multijet. And I used the same process as Alonzo, finding the event signature of the Higgs and then performing the cuts from Rachel. And I estimated the total TT bar events. And I used the W plus jet. I got the W plus jets estimate from Alonzo and used the TT bar estimates that I calculated to find the QCD fraction in the sigma region, which is the isolated leptons and high missing transverse energy. And so I was given the QCD fraction for the first 3 regions on the top, and I used that to find the sigma region QCD fraction was 6.3%, and it came out to total number of events 377.194 for QCD multijet. And in the bottom right is an example of data with background. And then on this slide there's a summary of all the events.
Hi, so my name is Abrar Kaja, and I was in charge of making a machine learning algorithm to isolate signal and background data. So the method I used was called the boosted decision tree, which uses a set of binary instructions to isolate data into different bins or like leaves of the tree based on their signal and background ratio. So the reason I used a boosted decision tree over like another machine learning algorithm like neural network is because one, it's the most practical and then like it's the most practical as in it has the most physical significance to our given data, and also it's the easiest one to run. So I ran my boosted decision tree on 4 variables: left jet ET, leading jet ET, missing ET, and transverse mass. And the first step in creating my decision tree was to use the Monte Carlo to first isolate or to create my different bins and create conditions to isolate events into my different bins. So using the Monte Carlo data, I looked to achieve the highest ratio or lowest ratio of signal to background. So that means that I either have a lot of signal in one bin or a lot of background in one bin. So by having a bin that's either as close to as a high ratio of signal or background, I can isolate the events clearly as signal or background. So I also attempted that in the middle of my tree to have similar amounts of events so that my ending bins aren't completely lopsided with a lot of events in one bin and then my other bins just being very small amounts of events. So after I created the conditions for my tree, I ran these conditions on the given data from the class, and this helped me isolate the data into the different bins. These bins were then given to Camden, who will tell you about his life formula.
Alright, I'm Camden. Now I was working on the likelihood bit. So since it was working with the Poisson distribution, our next step is to find the likelihood of our data. So here's the likelihood formula that we used for beta sub s. You can beat yourself, and also the mu value. And then here are different variables. N sub s is the number of signals expected from the standard model prediction. Beta sub s is the fraction of the standard model expectation. N sub b is the number of background events, and n is the number of observable events. Alright, so to the right here is our histogram. So all the data has been sorted into the bins, and as you can see, it's stacked on top of each other. And then it was scaled using the luminosity data. And then all the crosses represent the actual data values compared to just the values that we calculated from Monte Carlo. So since the calculations were really big and hard, what I did is I took the natural log of the likelihood function, and then on top of that I used Stirling's approximation, where the natural log of n factorial is around n multiplied by the natural log of n minus n. So that gives me finally negative mu plus n multiplied by the natural log of mu minus n times the natural log of n plus n. And this is done for each bin. Alright. Once that was done, I added it all together, and then I exponentiated it. And once I exponentiated, I used the left Riemann sum approximation to find the area under the curve. I found the center of the curve to be at 0.118 picobars, and then from left to right, one standard deviation, which is about 68% of the area, is from 0.11 to 0.125. So you find that sigma sub h is equal to 0.118 plus or minus 0.007 picobars.
Hello, my name is Eric Remacher, and I ran the frequentist counterpart to Camden's Bayesian methods. Essentially, I used the same likelihood formula as before, using the likelihood ratio of -2 times the log of that. That's all essentially identical to what Camden did. Using this, I then calculated the likelihood ratio for each bin, and I multiplied them together to give the total likelihood. Then, to calculate p-value, I generated 10 billion pseudo-experiments generated in a Poisson distribution centered around the expected background generated through a program, and the number that reached the likelihood that would occur of those 10 billion was recorded. This number was 0, as my computer was not able to effectively generate more than 10 billion pseudo-experiments in a timely manner. The 10 billion pseudo-experiments took 3 days to generate and calculate the likelihood for, and the next number that I was going to be able to do, 100 billion, would have taken a month, and unfortunately that was out of the scale of this project. Of those 10 billion pseudo-experiments that I did run, none reached the likelihood. However, the fortunate part of this is that means that the p-value is less than 1 times 10 to the negative 10th, as of the 10 to the 10th pseudo-experiments that were generated, not a single one reached the threshold, which is over 7 sigma of significance. The expected cross-section was 0.1 picobars. The actual cross-section was what Camden said. essentially the data was highly significant, and the probability of the data fluctuating to the levels that we saw through pure random chance alone, and not through some sort of interaction, is negligible. Qualitatively, bins 0.03333, 0.178571, 0.558824, 3.21429, and 3.6 repeating fell below expectations, while the 5 most signal-like bins, those on the right of the histogram, exceeded expectations, although they were still consistent with the data. As you can see, these 5 here, they all exceeded expectations, while several of the others did not.
Hello, I'm Andrew Salee, the expert on supersymmetry and how our experiment relates to the MSSM. So when we took all the results, we plotted the invariant mass of the B jets, what we saw is that there's a significant peak of mass at around 90 GeV. So fitting a Gaussian towards that, one can see that the mass peak is at 89.3 plus or minus 2.5 GeV within 1 standard deviation. So using those results, we calculated that the mass of the little Higgs, or theoretical little Higgs, would be at that mass. So then we utilized the relation above using a set mass of the Higgs at being 125 GeV, mass of the pseudoscalar Higgs boson, which we were solving for, the tangent beta, or the ratio between vacuum excitation values of the 2 Higgs fields, which we're also solving for, and setting mass of the Z boson to being 91.2 GeV. Solving for that, one can see that we found the parameter space for the mass of the pseudoscalar Higgs and for tangent beta, but there's an imaginary term in the lower bound for tangent beta. Now, that has no physical significance, so correcting for that, we see that this relation is fundamentally limited. However, still using this relation, we have the corrected mass of the pseudoscalar Higgs and of tangent beta. And the reason this relation failed is basically at mass of the little Higgs that are greater than the mass of the Z boson, or mass of the pseudoscalar Higgs that is greater than the Higgs boson, it breaks down. So, looking at these results, there are some problems. One, we failed to account for radiative corrections, which are substantial. Furthermore, LHC experiments have already shown that the little Higgs is greater than 92.8 GeV, and our experiment showed that it was below that. So there's our results seem fundamentally limited in this sense. Additionally, if the pseudoscalar Higgs was at the mass that we found, perhaps we would have already found it, as it is below the mass of the Higgs, which has already been found. So perhaps the particle that we found may not be the little Higgs at all, and something else that decays into 2 bottom quarks. Thank you very much.